How's it going, everybody? I want to thank you guys for stopping by and hanging out with me in this video. If you could go ahead and do me a huge favor and please like, share, and subscribe on the video, be much appreciated. Thanks, guys. How's it going, everybody? In this video, we're going to continue our addressing review section based off of the design exam topics, where we talk about create structured addressing plans for IPv4 and IPv6. So I'm going to go over the kind of the substance of what IPv6 is made out of, so how the addresses are built and things like that. I'll go through a couple of examples of how that works, and then we'll take a look at dealing with the address types and go through those details. We're not going to go super deep into that particular area, just as long as you are familiar with the different capabilities and the different options, you'll be in good shape. And then we'll be more or less focusing on incorporating IPv6 variations of the routing protocols and static routing, dynamic routing, that type of stuff when we go through the individual sections. So that's what we're going to be doing throughout this setup. So I'm going to go ahead and dive into the details here. We have our topology. We're not going to be doing anything with the topology just yet. We will be focusing strictly on just the theory in this video. So, and without any further ado, let's go ahead and bring this bad boy over. So these are some of my notes. I will be linking the notes in the description, so I'll put a Google Drive link there for you if you want to download these and take advantage of them. Feel free to be my guest. That's what they're there for. So that being said, let's go ahead and just generally talk about what it is IPv6 is, how it works and things like that. More of the addressing structure is what I really want to get across in this video. And then once you understand how it's built, then you'll be able to go, okay, well, I can allocate this and allocate that. It's really no different than IPv4 when you take a large address block and you want to carve that up into different ways and stuff like that. So we'll take a look at those details as we're going along. So I'm going to go ahead and get out of the way. So RFC 2460 is Internet Protocol version 6, where version 5 was skipped over. I'm not exactly sure how that worked out, but for the sake of argument, let's just pretend like there is no V5. V4 is a 32-bit address, as most of you are familiar with by now. If you're not, well, now you are. You're looking at about 4.3 billion addresses in total with 2 to the 32nd power. IPv6 is going to take that from 4 bytes to 16 bytes, so it basically quadruples the address space. And by doing that, it takes it from 32 bits to 128 bits, or roughly 2 to the 128th bit, or power, which gives you 340 undecillion addresses. So in other words, a lot. So what's actually kind of funny about this, and this is just my take on the situation, one of the problems that came up with the internet back in the late 90s, 2000s, this is just based off of some conversations that I've listened to on YouTube and people that I know in the industry that had a lot to do with the way that things are today. I won't mention any names here, but if you do any research, you'll know who I'm referring to. The conversation basically was that deploying IPv6 didn't really solve the problem that IPv4 had. It just basically gave it a bigger address block. So if you want to call that a solution, call it a solution. But in my opinion, if you're going to solve something, you're going to come up with a solution that's better than what's already there. Okay, so all the people that developed IPv6 really did was said, okay, well, 32 bits is obviously not large enough. So maybe they had the conversation of going 64 or 96 or 128. I don't know. I wasn't involved in those conversations. But one could assume that if this is the size of the address block, then what could be done differently? I don't know. I'm just an engineer that's trying to learn as much as he can. That's really at the end of the day all I'm doing. And I've just learned enough to this point where I can hopefully pass some of that information on to you guys in learnable and understandable terms. So did IPv6 really solve anything? In my opinion, it didn't. All it did was take the existing problem and basically push out its deadline until it needed to be adjusted. So in other words, if you've got IPv4 addresses and someone gives you a /8 range for a particular IP address block, that gives you 16 million IP addresses roughly. 24 bits is, three octets. So that's basically what a lot of organizations use today. They take NAT and they NAT a bunch of private IPs over to a single public IP to basically help with the scalability. Now, if you're talking just internet connectivity, 800,000 routes on the internet, that's a very small portion of the 32-bit range for IPv4. But, when you start giving every individual node its own IP, that's when you run into problems. And that's basically what IPv6 was developed to do. Instead of saying, let's NAT from a private IP address block to a public IP address block, and then you send your traffic wherever it's got to go, they're like, why don't we just give every device its own IP? That was the original intent. So guess what? That does away with NAT and things like that. However, that also introduces new security problems. So now you've got a PC that's connected directly to the internet. I mean, that's not going to fly, because now that CPU or that device isn't really meant to sit on the internet edge, right? It's meant to sit behind something. So the idea of every device getting its own public IP, it's great in theory, but in practicality, in today's market, to me, it just doesn't make any sense. I wouldn't trust a PC or a server being directly connected to the internet. It just doesn't make any sense to me. The piece that everybody needs to understand is, at some point in time, the IP address will be given to you, and you'll have to do something with it. Now, the formatting of the IPv4 address is real simple, right? You have dotted decimal. You have 4 Ds, right? You've got, each one of these Ds is represented by 1 byte or 8 bits. So 4 times 8 is 32. I passed 3rd grade. So when you go into hexadecimal, now you're moving away from just dotted decimal, or 0 through 9, and now, 0 through 8, or 7. Well, technically decimal is 0 through 9. But in hexadecimal here, in this guy, we're looking at Octal Math. So that's one thing, too, to pay attention to. If you didn't already know that, Octal Math is 0 through 7, right? So you've got 0, 1, 2, 3, 4, 5, 6, 7, which gives you technically 8 bits, because 0 is used, and then it stops there. So yeah, we'll just go with that. You have hexadecimal math, which brings into play both letters and numbers. So you have your 0 through 9, then you have A through F. We'll talk about that here in just a minute more. But if you look here, with the hex, you have all of these broken down. So basically, you've got 1, 2, 3, 4. So let's see, you do 2 here, you do 2 here, you do 2 here. So you got 1, 2, 3, 4, 5, 6, 7, 8. You got 16 bytes, because each one of these is 4 bits. I'm sorry, each one of these is 4 bits. Every H is 4 bits. So if you count 2 H's, that's going to be 1 byte. So because you've got the 4 bits in there, and the 4 bits, we'll talk about that here in just a little bit more detail later, that when you combine the two 4-bit nibbles, right, you got a nibble, and so a nibble is 4 bits, half of a byte. You take a nibble, I mean, it does correlate, and then from there you were able to break this out into 16 1-byte sections, right? And that's basically how that will come into play. Now, when the binary piece comes into play, this is where understanding binary is actually pretty crucial to understanding IPv6 and how hexadecimal comes into play. So when we talk about the binary piece, obviously we have 0 and 1, right? Where 1 means on, 0 means off. Where we take denoted as 10.1.1.1, where 1 octet is 8 bits or 1 byte. Each bit has a numerical value assigned to it. So same value here, 1 through 28 incremented by the power of 2. So 1, 2, 4, 8, 16, 32, etc., etc. We went over this in the previous video with the IPv4 addressing review video. So when we dive into the concept of the hexadecimal piece, we have to make sure that we understand that when we're dealing with it, we're only dealing with the first half, or what we refer to as the low order bits, meaning that they just have a lower numerical value to them. So, for example, if we look here, we have 2001 colon CC1E or CCIE colon 1. That would be a valid IPv6 address. You might be like, well, wait, it's so small. Well, yes, it is. And that's for good reason. You don't have to have it fully built out. There's actually a way to very easily what they call concatenate it, or to summarize it down to a smaller value. So because these guys right here are broken into 4-byte segments, we have each one of the broken down into 4-byte segments. I meant to say 4-bit segments, I believe. So each H is a 4-bit nibble. Those 4 bits also have a numerical value assigned to them, no different than up here. So if you understand this concept, right, where if you take 8 and 4 and you add them together, you get 12, which means if you have this is a 0, this is a 0, if all this right here is all zeros, and then these two are zeros, which means only the 8th and 4th bit are turned on, then it's going to be a value of 12 because those numbers correlate. So that would be a 12. Same thing if only these 2 bits were turned on, then you'd have a 3. If these 2 bits right here were turned on and nothing else was, you'd have a 192, so on and so forth. Now, with that being said, when you break these guys down, this is when you start getting into how the hex piece comes into play. So if you take 8, 4, 2, and 1, and you add them all up, you get a 15. So you take 0 through 9, right? You take 0, 0, 0, 0 is a 0. 0, 0, 0, 0, 1 is a 1. 0, 0, 1, 0 is a 2. 0, 0, 1, 1 is a 3, because you're turning on the second and first bits, which ties to a 3. So 2 plus 1 is 3. Well, once you're at the 0, 0, once you get to 0, or I'm sorry, a 1, 0, 1, 0, so basically like this, if you get 1, 0, 1, 0, so now that I've gotten all of them laid out, now you know what's going on. So with that being said, that's basically how this correlates. Now if you come down here to this IPv6 address right here, you can see that we have a 2, so you know this can be 0, 0, 1, 0. A 1 is here, then a 6 is 0, 1, 1, 0. A 3 is 0, 0, 1, 1. An F is all 1s turned on, so on and so forth. This is how you would correlate the first 2 hextets, if you refer to them as that, which is the first 2 16-bit sections, or 2 bytes. So the first 4 bytes of the IPv6 address are laid out like this. Now, once we get into the addressing types, this is where it gets a little bit more interesting. Now, if you look at RFC 4291, that's going to be the IPv6 addressing architecture. And if you look at 2.4, the addressing types come into play. Now, one of the first ones that you want to know about is going to be the IPv6 link local address, which is locally assigned to an interface. And every IPv6 enabled interface has a link local address. Whether or not you want it to have it, it's going to have it. So you might as well just deal with it, right? So when you look at this, the way that the address is broken down, you have FE80::/10, which means that when you take a look at this first, this F right here correlates to these 4 bits being turned on. When you look at the E right here, this correlates to these bits being turned on, right? And then when you look at the 8, you turn on the first bit, or this would actually be more like this. The first 3 of these are broken out like this. You have 1111, 1110, and then 1000, right? That's basically how that would work. So if that's not easy for you to identify, you have F, then you have E, and then you have 8. I realized that as I was typing these in, where I made my mistake. So you can see that we have these values right out here. Just let me rehash what I just said in case anybody missed it. So the idea is with the all F's right here, you're looking at all of the binary numbers being turned on, which gives you an F. So it's basically kind of like a broadcast. Well, effectively in this particular variation of it is a broadcast. But it's not actually broadcast in the concept of going into a room full of people and saying, "Hey, everybody!" It's not exactly that. You're just, in this case here, all ones indicates an F is used, but it isn't specifically broadcast in that particular case. But I just wanted to, it's not a broadcast, but some people might incur it to be. Now the E is the same thing. We have 1110, and then you have the 8, which is the 1000. Now again, 169254, if you don't have IP, if you DHCP is not working, or you're going to go with a static addressing assignments. Now you can use this for SLAC, the stateless address auto configuration capability, neighbor discovery, and router discovery. These are going to be used quite frequently. As a matter of fact, you'll see this when we get into dynamic routing with OSPF, EIGRP, RIP, static routes, that the link local address will actually be your pointer to the next hop. Because on the link, they're both talking to each other, right? So on the same physical link between two different devices, switch, router, whatever it might be, you're using link local addresses. So you don't point to a public IP, a public IPv6 IP, to your next hop when you're routing internally. You are using the directly connected link to get to where you've got to go. So you'll see this when we get into dynamic routing, because we are going to be taking a look at that in a lot of detail once we get into the IGP section and how that comes into play. Now, when it comes to IPv6 site local, nobody could really agree on what a site actually was, because in my opinion, a site is a physical location. Okay, so but you might think that a site is just a geographic area where multiple buildings might exist, right? So take a campus network, like a college or a school, or you go into a mall, for example, where you've got maybe the mall. There's a couple of malls in the area that I live in. One of them is outdoors. It's called Bayshore Mall. It's located in downtown Milwaukee near the lakefront. Well, if you go to Bayshore Mall, there's a portion of it that is exterior, which means it's outside, which means you're not covered by some sort of overhead walkway, meaning that you're going to have, like, it's Bayshore Mall, but there's multiple buildings inside of Bayshore. So to me, a location or a site is a physical building. If you have site 1 on at this particular location, you might have a, that's basically how I correlate it. But that's how the technicality for me comes into play. You may not look at it that way, and that's completely okay. But because you and I'm intentionally taking the other path, so that you could be like, well, a site could be multiple buildings, Rob. And I'm like, you know what? You're right. I'm not saying you're wrong. But because I'm going to be the devil's advocate, and you're going to be the person that thinks, you're smarter than me. So that's why the unique local concept was brought out. Okay, so unique local takes the concept of site local and it basically envelops it. It says, you know what? We're going to go ahead and just take the site local addressing block, so the FCC/10. We're going to take that and we're going to absorb that into the unique local, because you can see if this number is smaller than this number right here, it means that address block is bigger. So it's going to absorb the other address range, which gives you the ability of saying, you know what, we're going to go with unique local. Unique local says, you know what, we're no longer going to tie it to a site or a geographic location. We're just going to say, okay, if you need IPv6 addressing internally, guess what? We got your back. And that's basically how this comes into play. So with unique local, RFC 4193, you have the FC00::/7, where in the F right here, you have all Fs. And then in the C, you've got the 4 and the 8 turned on, the 2 and the 1 are turned off, which gives you the C. This is equivalent to the RFC 1918 address space, which is going to be the 10/8, the 172.16/12, and the 192.168.00/16. It's pretty straightforward stuff there. Now, this is not routable on the internet routing table. So this is the point in time when you would actually have to NAT from private to public. Now we'll take a look at that in the NATing section when we're talking about IPv6 and the transition mechanisms that are out there. Now there are other ways to do this. So how much IPv6 is out there? In my experience, not a lot. There are some providers that are using IPv6, others that are not, and it's more prevalent in the UK, the EU, European Union, Asia Pacific. Most of the customers that I worked with that had locations outside of the US, there was a sprinkling of IPv6, but most of the time internally in the US, v4 all the way. So just be aware of the capability. Now there are some Nat specific capabilities like Nat PT, protocol translation, where you can go from v4 to v6 or go from v6 to v4, and we'll take a look at those as well when we get into the advanced services. So when we get into services, we'll talk about Nat there. That'll be a long ways down the road for us because we have a bunch of other topics to talk about before we get to that point. Then we have IPv6 global unicast addresses. So for those of you that are familiar with IPv6, this is going to be the 2000:3 address range. Now, the way that this is concatenated is you have basically the left half, or the high order bits, so from the 128th down to the 64th, you basically have all network. So this is going to be reachability on places on the internet. And a lot of times what will end up happening is the part that I'm highlighting here, the first 48, this is going to be allocated down to the service provider level. So the service provider is going to get a /48, and then what they'll do to a customer is they'll hand out /64s, and they're going to have this entire address range. There's a lot of addresses that can be allocated from just this 16-bit section. So don't think of it like, wow, that's not very much. You'd be surprised. So just think of it like that, where you have lots and lots of work to wiggle room. And this is also the same part that you would subnet. We're going to talk a little bit about subnetting IPv6, but not much. The idea is no different than IPv4 when you're dealing with the breakdown for this guy right here. So you have this N right there. Remember, this right here has 4 bits in it, 8, 4, 2, and 1. So which means that all of this right here on a per digit basis, so one of those N's out of those 4 N's, all of this applies to it. So if I want to do some subnetting, I could come in here and give the first range out, then I can give the second range out, then the third range out, then the fourth range out. You're giving a lot of IPs. It's like trillions of IPs out to people when you do this. So the Internet Assigned Numbers Authority, IANA, the few times that I've worked with them to give a customer a /48, you just have to provide a little bit of justification, and boom, they give you a /48. They don't even bat an eye at it. They just give it to you. So with that being said, just think of that in that particular case. Now the back half, or the low order bits, this is what gets assigned to the endpoint, whether it's the laptop, the PC, the printer, the server, whatever. This gets an IPv6 address. Now, what's going to end up happening is out of the gate, if you don't do anything, what's going to end up happening is this address right here is going to be automatically assigned based off the MAC address of the interface. So what will end up happening is the EUI64, or the enhanced enhanced user interface, or whatever this EUI stands for, I can't remember off the top of my head, basically gives you, it takes the 48-bit MAC address from the interface, and it says, okay, I've got 48 bits, I need 16 more. So it basically takes the 48-bit MAC address. So if we were just to take this, for example, and let me go ahead and just adjust this real quick. Let's say we have 0101.02.02.0303. It basically takes this guy right here, it chops it in half, it chops it in half, and then in between these guys, it adds in some padding, 16 bits of padding, which is FFFE. So it takes this padding, it injects it inside of there, so your IPv6 address actually becomes like this. It becomes 010102 FFFE 0203, which gives you your 64 bits, right? Because you need one, this is 1 bit, or 1 byte, this is 1 byte, this is 1 byte, so it's 3, 4, 5, 6, 7, 8 bytes. So 8 times 8 is 64, which means it gives you your host-specific information right there. That's how that's broken up. Once you do that, this guy right here, this is the, and remember those most significant bits are the high order bits. What's going to end up happening when this happens is what's going to happen is the universal local bit, the 7th most significant bit. So if you were to take this and look at it, if you were to take, for example, you take the 0, 0, 0, 0, so 0, 0, 0, and then the 0, 0, 1, that's what 0, 0, this would be the 0. And then you have this guy right here would be the 1, right? What's going to end up happening is when you do this bit right here, this guy right here is going to get flipped. This is the 7th most significant bit. This bit gets flipped it gets turned on. So your MAC address will no longer be this. It won't be a 0. Let's back this up just a little bit. It'll be a 0, and then which will be a 0, 0, 0, 0. And the 1 will no longer be a 1. It'll actually be a 3, which will get turned over, which will be a 0, 0, 1, 1. Because now this bit has been turned on. This is the 7th most significant bit. It gets turned on, which becomes a 2. So 2 plus 3, or 2 plus 1 is 3. And that's where that MAC address will become. So your MAC address would no longer be 0, 1. It would now be a 0, 3. If you see the MAC address change, then you know where that came from. So how would you verify that? If you do on this command, if you do on this on that interface, you do a show interface gig 0/0, for example, pipe include BIA, burned in address, so the layer 2 header. If you look at that and you get this guy right here, you go ahead and just adjust this real quick. You get this, and this is 1, and then all of this has been removed. Right? So if your MAC address shows up like this, but you've got EUI64 turned on, another device does the same, is going to do a show ARP or show MAC address table or something like that, and they're going to see this. This is what they're going to see. Let me go ahead and fix this up real quick. This is what they're going to see. And you're like, well, that doesn't look like a MAC address. It technically isn't a MAC address. So what you're going to see is the 03, the FFFE. This is going to be the address, right? So this is what you're going to see from the remote side. So this is going to be the local side, right? This is what the MAC address is going to be configured at the interface level or have been allocated for that device. This is going to be the IPv6 the host portion of the IPv6 address for that particular interface that you're pointing towards that use EUI64. That's where this is going to come into play. This was a really difficult concept for me to understand when I first learned it. I was like, this doesn't make any sense. Why would they do that? Well, somebody thought that would be a great idea. And then you obviously have the MAC to the conversion here to go through, which we just went through and explained how it broke that down. And then you have the temporary addresses, obviously, which is your Slack. And then you have address resolution protocol. And what I'm going to do is I'm going to stop here because now we're getting outside of the addressing range, right? So addressing is pretty much stopped. And now we're getting into the neighbor discovery and the neighbor solicitation, router advertisement, router solicitation. And we're going to actually demo that on the routers. So I'm going to show you guys how that looks and what that does and all that type of stuff, because those details need to be understood as well. But this is basically what this means. So IPv6 neighbor discovery and router solicitation and things like that uses ICMPv6 to exchange the information. So we'll take a look at exactly how that works and go from there. But that's IPv6 addressing in a nutshell. So there's more. That's pretty much everything you need to understand about it in terms of the operations, and we'll take a look at how that works as we go along. If you have any questions, leave me a comment in the comment section below. I want to thank you guys for stopping by and hanging out with me, and I'll catch you guys in the next video. Please make sure you like, share, and subscribe, and we'll catch you guys in the next one.